Now that we've got a basic understanding of Lewis structure, how our bonds connect, and something about the arrangement of those atoms in space, we now want to understand something about the functionality. What happens when we bring things near each other's? So, near each other's, that's fun. When we bring two atoms near each other, we may notice that we can generate a bond. So as I bring an oxygen near a hydrogen, I might start to generate a bond. Well, why would I generate that bond? Okay. The oxygen comes in with its electron, the hydrogen comes in with its electron. And what eventually will happen is that the oxygen, with its electronegativity, starts to see that electron, and so the electron kind of starts to shuttle towards the oxygen. Okay. At the same time, hydrogen is sitting over here and being like, you know what, electron? Go have fun. Go share over there with that oxygen. And it's that balance of going back and forth between them that generates that bond. Well, what characteristics of oxygen said, give me that electron, and what characteristic of hydrogen said, yeah, it's okay, let's share? Okay? That comes down to our electronegativities. And it is the balance of our electronegativities, finding a negative and putting it near a positive, that allows us to predict something about our reactions and our physical properties. And that's kind of what we're going to be getting at in here. So you need to be familiar with the trends in electronegativity. That trend being, fluorine is our most electronegative, and then hydrogen is our least. Well, is that perfect? No, it's not perfect, so don't quote me on that. But it gets you pretty darn close. If you look at the actual numerical values, it can be helpful to go through and memorize those if you really, really wanted to. Okay? But it's not super worth it. If you've got the trend nailed down, you'll probably be fine. Okay? So that's what we're going to end up trying to work with, is dealing with that trend and how can we predict the things that come out of it. Before we even do that, what happens when you bring these atoms near each other? Say a hydrogen near a carbon, or a hydrogen near a nitrogen. What kind of bond do we have? Because there's a difference in electronegativity in each of those cases, we end up going through and naming them something else, because the reactivity is different. So if we look at a sigma bond between a hydrogen and a carbon, also known as a single bond between a hydrogen and a carbon, we end up with an alkyl group, sometimes referred to as alkanes. Okay? If we bring a carbon near a carbon, we also have an alkane, okay, as a single bond. What happens is we start attaching other things nearby? Well, hydrogen to chlorine, we have a strong acid. So the difference in electronegativity ends up changing our reactivity enough that we come up with a new name. And you probably aren't even remember your names for acids, just because they're so reactive. Okay? Whereas the alkyls, most people don't remember or know anything about our alkyls or our alkanes because they aren't very reactive. And it's that very nature that we end up trying to manipulate and change when we work in organic chemistry. The last little functional group we could throw in there is sometimes the bond between them ends up being a pi bond. So if we take a sigma and a pi bond, we end up with a double bond. In the case of a double bond between a carbon and a carbon, we have an alkene, or potentially an alkyne if it was two pi bonds, carbon and nitrogen, an imine, carbon and oxygen, carbonyl. So what we're trying to do is just kind of classify some information. What happens if I now start to bring these different bond types near other different bond types? Will those different bonds interact with each other to generate new types of interactions? Well, yes, unfortunately they do. And so we end up with a ton of different possible functional groups. And we already talked about some of these, saying that you needed to know and memorize these functional groups. For instance, this semester we'll be spending a lot of time looking at our alkanes, alkyl halides, alkenes, alkynes, our alcohols, and our ethers. So you should really commit to memory what those functional groups look like so that you have some idea of then the next things that we'll be looking at, their reactivity and their physical properties. The rest of those functional groups are really kind of relegated to second semester. Okay? Is that all of them? No, but these are our primary functional groups. These are also the ones that you end up being more responsible for when it comes to nomenclature. Look for an online video on that. Okay? So, now the fun part comes in. Before we can even get a reaction, we need to have an interaction. And this is a challenging concept for most people to acknowledge, because what they look at is they say, well, there's reactions and there's interactions and they're two separate things. That's not true. Okay? What we are looking at is how two atoms, regardless of the rest of their environment, how those two atoms interact with each other. So what we're going to do is say, okay, I now acknowledge that I have a compound. In this case, I'm going to acknowledge that I have sodium chloride. I want to know how that sodium chloride is going to interact with another molecule. Okay, well, hopefully we can determine that it has, whoa, please don't do that. Oh, actually, I'm just going to click through that. We can determine that there's really two possible types of interactions. Okay, I could have them align where the chloride matches the sodium, or I could have them align where the chloride matches the chloride. Well, which interaction ends up being more favorable? And it turns out that the top one is more favorable. That's an interesting question. Well, why would the top one be more favorable? That's a question for lecture. So think about it, and when we get to lecture, you should have a solid answer for it. What happens in, say, some of the other cases that I then just quickly erased? Let's see. Let's not look at that one. Let's look at the next one down. Okay. What kind of interactions might I predict in this situation? Which interaction will be favored? The top interaction or the bottom interaction? It turns out, really neither. Neither is favored, neither the top nor the bottom. That's a bit odd. We all of a sudden have a switch in the type of reactivity. And in the last potential cases that are now hidden over here, but if we reveal them, if we look at how the OH bond interacts with a like bond, and we look at those interactions, it turns out that the interaction that is favored is, again, the top one. So what patterns are coming out of this that we can start to predict? So number one, look at the molecule we're starting with in all cases. Okay, in our first example, we are starting with sodium chloride. What type of bond is present in sodium chloride? Remember how we went back and we asked what are the three bond types and you needed to be able to acknowledge them? This is why. We have an ionic bond. Well, in the next case, what type of bond do we have present in CH? Well, this is our nonpolar covalent bond. And in our last case, what do we have? We have a polar covalent bond. So that's interesting. We're starting to get different interactions between these different molecules because we have different bond types. The classic, or the biggest difference, is looking at the covalent one. Why does the covalent one not favor one over the other? Well, as a covalent bond, what charge, or where do the electrons in that bond spend most of their time? Fair enough, evenly on both sides, which means the carbon and the hydrogen end up being zero charge, which means when we go to our other molecules, we end up with zero charge. If we have no charge on the atoms, is there any reason for those molecules to interact? Well, no. What does that mean? The interaction we would predict here would be very weak. Okay, at best, weak to nil, or null, however you want to spell it. Okay, not existent. If we go through and look at our ionic and our polar covalent, what happens in our ionic system? Well, sodium being so low in electronegativity completely gives up its electron to the chloride and carries a formal charge. This applies back to the other molecules, and what we end up noticing is that in that top interaction, I can cancel the negative and positive by putting the positive near the negative. In the bottom example, I would end up doubling the negative charge by putting the negative next to a negative. That's not a good system. So the top interaction is favored. What happens in the polar covalent system? Well, oxygen is still more electronegative than our hydrogen, so it starts to steal electrons, but it only starts to, so it's partially negative. Our hydrogen carries the partial positive. We scale this to our other molecules, and we end up noticing that we end up with the same type of interaction, or the same type of system. In the top situation, I get the charges, the negative and positive, to align with each other in a way that the charge cancels. In the bottom case, I get positive to positive. That's not a good system. So what we're looking at is, how do we get these interactions? Well, we got these interactions by looking at the bonds of our molecules. How were those atoms individually affected before they came into that interaction? Okay? And one of the things that you'll hopefully start to notice is that we get different levels of strength within each of these. Okay? So what you need to be able to do is to look at a compound, see its bonds, and say that bond will generate this type of force when it gets put into an environment with other molecules. To do that, you need to be able to see the difference between these and acknowledge what those definitions are. So I'm going to take advantage of pause here for a moment. With our quick definitions for our bonds, ionic being metals and nonmetals, our covalence being the same type of element to the same type of element, and carbon to hydrogen, and our polar covalence being whatever's left, okay, we can now start to predict something about our intermolecular forces. Well, in our covalent system, if you remember from the other side, we had a very weak interaction. So this ends up leading to what we call our London dispersion force. Okay? Or, as you may have heard before, a van der Waals attraction. Okay? And this is kind of interesting. The other ones pick up actual sort of real names, and this one picks up a scientist's name, because we thought that interaction was so infinitely tiny, there's no reason for it to exist, that we called it zero. Van der Waals came along and said, no, you're wrong. It actually has some importance. Because it has that importance, we decided to tie his name to it, and I have no idea where the London comes from. Let's just say he was in London when he put it together. The dispersion has to do with the electron clouds. Our electron clouds are shifting, giving us temporary or momentary dipoles, which give us the weak interaction that is characteristic for our London dispersion. So these are now our weak interaction, neutral to neutral. If we look at the other extreme, our ionic situation, metal and nonmetal, well, what ends up happening is we get a very strong attractive force, okay? And that strong attractive force typically carries a couple different names. The least useful name, but is still commonly used, is referred to as ionic bonding. There's an interesting issue with calling it ionic bonding. We're referring to a force. Well, where did that force come from? It came from a molecule that had an ionic bond. Not the ionic bond force, but the ionic bond as a bond. Okay? So as a way to kind of clarify that, we can sometimes refer to it as an electrostatic force, which is ultimately the same thing as saying it's ionic. What happened when we get to our polar covalent system? Well, in the polar covalent system, we ended up with two molecules that had partial charges, and those partial charges aligned with each other in such a way that they would kind of cancel, just like we saw in the ionic system. Okay? Well, this first molecule has two poles, a positive and a negative, known as a dipole. If I look at the second molecule, it also has a dipole. So the interaction that is happening between two molecules with dipoles is now referred to super originally as a dipole-dipole force. This is some kind of intermediate force, or intermediate strength, if you will. It is definitely stronger than the London dispersion because it actually has some partial charge associated with it. It's nowhere near as strong as our electrostatic because the electrostatic had full formal charges interacting with each other. Right? You'll notice there is a fourth thing listed on here that I've not directly explained, okay? And that is hydrogen bonding. You'll also notice that hydrogen bonding is offset and not directly tied with an arrow. And that's because the arrow that it gets tied with is the dipole-dipole. If we find a molecule that has a polar covalent bond, it will generate a dipole-dipole force. That is known. The next part is then what happens. We will look very closely at that interaction and we will ask ourselves, is there a hydrogen present? If there is a hydrogen, I then want to ask myself, is that hydrogen bound to oxygen, nitrogen, or fluorine? If the hydrogen is bound to fluorine, oxygen, or nitrogen, then I have hydrogen bonding. Well, why name this special force? Well, notice the order I put it in. Hydrogen bonding is actually such a strong force that we've subcategorized it outside of the dipole-dipole force because we can get some pretty weak dipole-dipoles. Hydrogen bonding is massively strong. It is almost an electrostatic force. That's how strong it is. Well, how could we figure that out? Well, fluorine, oxygen, and nitrogen, look back at your periodic table, are the most electronegative elements on our periodic table. Hydrogen is one of the least. We get the largest difference in electronegativity with those atoms. That's going to generate a very strong dipole, which then gives us a very strong force. So why look at all of these forces? Okay. Well, these forces determine all of the physical properties that you've already been expected to look at. And I know for a fact you've seen these in 151 and if you took 130. Okay? Most people just kind of gloss over it and ignore it. Melting point. The point at which a solid turns to a liquid. Well, what's keeping it a solid? There are intermolecular forces keeping our molecular compounds solids. So what happens when I go to a liquid? I break all of the forces that are holding, or most of the forces that are holding those molecules near each other, and I now have a liquid. The stronger the force, the higher the energy needed to break that force, so I get a higher melting point. What happens with the boiling point? Same idea, except in the boiling point, we're now breaking every single one of the forces and we're fighting against atmospheric pressure. Okay, so boiling point is the point that I break every single force and I exceed atmospheric pressure. That's now our definition of our boiling point. The stronger the intermolecular forces, again, the higher the boiling point. The higher our atmospheric pressure, the higher the boiling point, because I need more energy to break against that. The next fun part, solubility. Your rules for solubility, like forces dissolve like forces. Why? Because they're trying to interact with each other. The more similar those forces, the more likely they will interact. So it's kind of a really neat process that we can find all of these things in it. This picture is supposed to illustrate that. If we can identify that we have an ionic bond that's, say, I don't know, an orange ionic bond, that will correlate to an orange ionic force. Okay? Same idea with our polar covalent system. If I have a green polar covalent bond, that will correlate to a green dipole-dipole force. I will then evaluate, do I have a hydrogen bound to nitrogen, oxygen, or fluorine? If I do, I've got hydrogen bonding. This gives me some information relatively quickly about the types of interactions that molecule will have. Massively important. We will apply this when we get to the lecture, and we will apply it when in lab. Hopefully this will help you get through the lab assignment that is due this coming week.